Right. Does anybody doesn't understand Russian in the audience? Okay. So like this, I will speak in English. So the Magnonics is very relatively young and fast development part of physics. And the Magnonics is some kind of development of general process of transport and some kind of modulation of this transport by external forces. The first one was, of course, electronics, when we have the electric current, and many different applications of this electric current can be used for because of the like transistors or some other things, logic, and so on. Later, it was found that in addition to the electrons and different methods of application for electrons, there was a possibility to use the spin part of the electrons, somehow to change the parameters of electric current. So this equipment based on this method was named the spintronics. And later, or even at the same time, there was developed other idea. It is the magnonics, when the magnetic moment transport without electricity, without the electrons. So this is the transport of magnetic moment in dielectrics. There are some few examples of this magnonic equipment. For example, usually it was used the jig, monocrystal films, and magnons have been created in one side, then propagate along of this sample and get the power out from the other antenna. This current of magnons can be changed by magnetic impurities, for example, or by pumping of other magnons in some kind of the caves, which destroy the current of magnons. So this is all examples of magnonic, where the magnons used as a magnon gas of magnons. So for yttrium ferrite granate, there is 3 branches of resonance, and for this equipment usually use this one branch, which is correspond to the magnetic field in plane of the film, and the spin waves moved along of this field. So this is so named backward volume magnetostatic spin waves. They have the minimum of energy. That is why they are very stable in the conditions of some kind about 10⁻⁵ inverse millimeters. There is even some examples of logic based on the magnonics applications. For example, here is the generator which create magnons. The magnons come through the 2 parallel plates of yttrium ferrite granate, and finally they are combined in the detector. And if we have in addition, there is some additional current which can be close the flow of magnons. So if we have any current in this gates, then we have full signal here. If we have one of current still there, then we still have the signal here. And only if we have two current in both sides, then we have no signal here. So this is some kind of logic. It's just samples which are not important for my presentation. What is important for my presentation is the next one. Here is always speak about gas of magnons, or some kind of magnons which can be considered as the sticks. You know, the magnetic phenomena is quantum phenomena by definition. But approximation of average field working, and then all equations can be, all properties can be explained just like a solid body rotation. Solid body is the magnetic moment of ensemble of magnetic moments. Indeed, there is not only the liquid or gas usual magnetic phenomena. There is also the cogherent phenomena. The first cogherent phenomena have been observed in Kamerlingh-Onnes in 1908. It was superconductivity. Second one was observed by Piotr Kapitsa in 1938. It's superfluid of helium-4. Then these beautiful guys have found the superfluid of helium-3. Helium-3 is the isotope of helium-4 with the magnetic moments. And they have superfluid state, very, very complex, because superfluid helium-3 is not only superfluid, but it is the magnetically antiferromagnetic liquid crystal. So the transition to superfluid state appears simultaneously to the transition of antiferromagnetic state and liquid crystal. So somehow helium-3 is one of the best examples of antiferromagnet, because the relaxation is extremely slow. So magnons can live very long time. Secondly, the magnetic properties doesn't relate to superfluidity itself, because the Hamiltonian, magnetic part of the Hamiltonian is perfect antiferromagnetic Hamiltonian. Helium-3b, which have place in this diagram in this corner. So here is the pressure, temperature, this is 1 millikelvin, and the magnetic field. So helium-3b exists in this corner, and all other is helium-3a. Helium-3b is 3 sublattice antiferromagnet. It's very exotic. And because of these properties, it was found the coherent quantum state for magnons in helium-3. It was done in 1984 in Institute Kapitsa under supervision of Andrei Viktor Stanislavovich Borovik-Romanov. It was made by a young team, which was created by Piotr Kapitsa for get Soviet superfluid helium-3. We have succeeded this. And just next step was discovery of spin superfluidity, the quantum transport of magnetization. And so it was in 1984, and then 11 years later, that was observed atomic Bose condensation. So there is not only this example of the superfluid or just condensed matter, quantum condensed matter. There is also quantum condensed matter in nuclear superfluidity in pulsar, nuclear stars, and also the universe, our vacuum, is considered as the quantum state. Why it's quantum? Why we have seen nothing from the vacuum? Because like in helium-4, for example, for creates any excitations, you need to move with velocity about Landau velocity to create excitations. is smaller velocity, there is not excitation. So some features who can live inside of helium-4, superfluid helium-4, can move, and just thinking that there is only excitations, rare gas of excitation, nothing more. They don't feeling the helium-4 atoms itself. Like in our universe, we don't feeling these Planck atoms with huge energy, which are surrounded us, but we have not feeling it because it's a covariant quantum state. Okay, so let's go quickly for just to explain the Bose condensation, which is simplest and best way to explain is the cold atoms. In cold atoms, what we have the number of atoms in the trap, magnetic trap, and its atoms cool down by some light, which removed from this ensemble the atoms who has a high velocity. It's the same like we have cooled down the coffee cup, so we just make a wind on the top of it. So finally some atoms removed and some other cooling. And there is also just very simple approximation coming from the Bose statistics, that at some temperature, which is about this value, you see this only density of atoms and temperature, and mass. So temperature, density of atoms, and mass of atoms. You can see that if temperature higher than this limit, we have gas. If this temperature is lower than this limit, we have the macroscopic number of atoms on the ground state. Just not enough space to put all atoms in different states. So we have ground state with one macroscopic number of atoms. And here is just very nice picture which shows the distribution of atoms in this trap. Here in the left is the density of atoms in units of Tc. You see, you have cooled down. As a result, the number of atoms decrease and Tc decrease. So it's left scale. And right scale is the temperature of this cloud of atoms. And you see, if the temperature is above than this Tc, then we have just clouds of atoms. And below, then we have the Bose condensed state. Now, let's go to the helium, to the magnons and helium-3. Experiment which was made more or less per hazard was done in 1984, and here is just shown the more demonstration of this experiment. And this experiment we have used the the cell about 10 millimeters long, and we have put just big gradient of magnetic field. So 600 hertz on the dimension of the cell. And frequency is 1 megacycle about. And what we have seen, if we have used the normal helium-3, then we have seen induction decay, which drops down just corresponding to something 0.002 second, just inverse of this broadening. So usual induction decay signal. What happens if we go to the superfluid conditions of helium-3? What we have seen exactly the same induction decay signal. So all magnetization, deflected magnetization, completely defaced. And then, without any second pulses, without Ekhan, the system itself spontaneously became coherent again. So the system reestablished the ordering of magnetic precession, even in the conditions when it was completely lost memory about frequency and about phase of excitation, because the frequency is different. Of course, phase is completely arbitrary. So this is an example of Bose condensation of magnons, very clear, which correspond all properties which are demanded for to show that it's Bose condensation. So you see the signal later decay because magnons evaporates, just the same as atoms in the trap also evaporates. So atoms back state leave something about parts of second. The best one is just now a few seconds. In our experiments, you see we have signal here just half a second on the frequency of 1 megacycle. So it's very, very, very coherent system. And decay, it's decay not because of some process of decoherence inside. It decay because just number of magnons decay. So this is a picture of this guys. Just after a few months of this discovery. And this is the behavior of the signal. We just measure instant frequency for any point. You see, this is a recording in this stroboscopic recording. So between each point here is many, many oscillations. Otherwise, we cannot make the good, recording of the signals. By the way, this is the first application of fast memory for superfluid helium-3, because the fast memory recorder was just start to be produced in England, and Kapitsa have got one of the first this equipment for to use in his laboratory. And I recognize that it will be very important for us to have fast memory recording for to see all parameters of induction decay, not only amplitude. So I come to, I visit Piotr Kapitsa and ask him, is it possible to use this equipment? He said, okay, Yurii, you can just come at 9 o'clock in the evening, take equipment, write exactly all connections and all positions of the valves, and it should be back at 9 o'clock in the morning with exactly the same conditions as you have taken. So as a result, we have working from 9 o'clock of the evening to 9 o'clock of the morning. But it was the first application of this equipment to the superfluid helium-3, and what was important, that we have found that frequency of the signal changes with time. So at the beginning it has a frequency correspond to the highest field in the cell, and then go down, down, down to lower field of the cell. So what is this phenomenon, Bose condensation of magnons? You see, if you have thermal equilibrium magnons, its chemical potential is equal to 0. If you are cooling, you have a number of magnons just going to 0. It was always, the density of magnons will be always below the critical density for any temperature. So you cannot have Bose condensation for thermal magnons. But atoms are not also thermal particles. It's the excitations of the world, of the cosmic world, and it's just living too long time. That's all. So, if we have slightly deflect magnetization, we have in addition to thermal, we have also excited magnons. But if we are working at the small angles, then we have just number of magnons here near K equal to 0. And we can use it as the Magnonics gas. To get the Bose condensation, we need a big angle of magnons deflection. In this case, you can apply the same equations for the Bose condensation: temperature, density of here magnons, and mass of magnons. Of course, magnons should interact each other. So mass appears because of interaction of magnons between each other. So it's definitely non-linear phenomena. And, so if we have deflect on some big angles, we have additional interaction which changes the energy. But here you see number of magnons can be very big, up to Avogadro number if we have deflect on 90 degrees. Mass is very small, so temperature for different parameters is very different. And for the example, for superfluid helium-3b, we have a Tc, which is something like 10 Kelvin. And our experiments are made in 1 millikelvin. So you see we have 4 orders of magnitude below Tc. As soon as we have created some number of excited magnons, they immediately go to the Bose condensation because temperature Tc is much higher. So, again, I should say that Bose condensation of magnons which are interact each other, which have repulsive interaction, because if you have attractive interactions, then we have instability of homogenization. And we can make some kind of the parallel between ideal gas and magnons. For example, we have ideal gas which corresponds just paramagnetic. We have quantum gas which atoms interact each other, and analogy is the magnetic ordered materials. And but spin waves are some excitations, not coherent excitation. But then finally, in the cooling, we have Bose condensation or superfluidity when all ensemble of atoms has exactly the same wave function, presented exactly the same wave function. And in case of the magnons, we have Bose condensation of spin waves. So all excitations describe exactly the same wave function. So this is phenomena of Bose condensation. We can show that just computer simulation to show how it develops the Bose condensation of magnons. For example, here we have this cell with, for example, here this 1 to 3 millimeters, and magnetic field has a gradient inside. So this is a bigger field, this is a smaller field. If we have pulse of 90 degrees, after some transient process, we have the region when the magnetic moment are vertical, density of magnons only thermal density, and other side we have domain when magnetization deflect, particularly in 104 degrees, it's a magic angle, where all magnons here precess homogeneously with the same phase, and this is the Bose condensed state in helium-3b. We can also do it differently. If we have pump radio frequency field, for example, correspond to this magnetic field, omega gamma h in this point, because you remember we have the gradient of magnetic field. So after some transient process, we have exactly the same phenomena. We have exactly the same distribution of magnetization. So what happens? What happens? In the first moment, we have deflect all magnetization. After some time, the gradient of phase of precession appears, so system completely dephasing. But gradient of phase means the transport of magnetization, the spin supercurrent, the current which appears due to the difference of phase of precession. And this supercurrent transports magnetization in one corner from the other corner. So magnons transport from here up to the lower field. It's energetically favorable. So finally, when they come to the angle of deflection 104 degrees, the additional frequency shift appears, which stopped the further increase of density of magnons. And as a result, we have this two-domain structure. Now experiment. We can make two. First of all, if we have pump slowly, very small radio frequency, which keep the number of magnons constant, just to add some magnons which compensate the relaxation of number of magnons. Then we can keep the state permanently. And also in this case, this state, which is ground state, will be coherent to the small radio frequency pumping. Now what we can do? We can make a channel between two and see what happens in this channel if we make the gradient of phase this precession and this precession. What should be? There should be current, because there is a gradient of phase. In this current should transport of magnons. So this is current of magnons which transport Zeeman energy. As a result, because of this additional transport of Zeeman energy or number of magnons, it means that in one cell the adsorption of RF pumping increase and in other decrease. Here is the gradient between two electrode, difference of phase of precession. And here is the difference of energy, which adsorbed in one domain and adsorbed in other domain. You can see in one domain with increase the current, increase of gradient along this channel. In one domain, the frequency, the power increase, and other decrease, because the current moved from one side to other side and transport additional energy. Furthermore, in some conditions, we can get the conditions when in one side energy adsorb and other side it's radiate. So magnons moved by superfluid current from one cell to other. One adsorb radio frequency energy and other is radiate radio frequency energy. So this is typical. This is magnonic transformer, which transport of magnetization. Furthermore, this is measurements of critical current. As usual, superfluidity has a critical velocity, Landau velocity, and we have measured it. Furthermore, we have put some orifice in the inside of this junction, and this is the experimental parameters. So orifice was 0.4 millimeters. And we can have also the coherent lengths, which is changeable, because coherent lengths depend on the difference between Larmor frequency here and radio frequency of pumping. The bigger this difference, the smaller coherent lengths. So we have made the coherent lengths which correspond to the whole, and then we have very nice Josephson effect. The current determines by difference of phase between two sides. Then if we have decreased the coherent length, so it means that it became smaller coherent length, and we have seen the distortion of the Josephson effect. And finally, when the coherent length is very small, we have the phase slippage. So all this phenomena from Josephson to transport on the channel is shown here experimentally, observed, and if you see it's 88. Now, the same phenomenon we have seen in other superfluid helium-3, helium-3A, which is classical to sublattice antiferromagnet. Usual superfluid helium-3A is easy plane antiferromagnet, but and the homogeneous precision is unstable because of the attractive interaction between the magnons. But if you have, by some additional structure, change helium-3A from easy plane to easy axis antiferromagnets, then the interaction between magnons is repulsive, and as a result, we can see the formation of Bose condensate. What is important? Because in this case, we can do it by continuous wave NMR, and property of this, very clear property of this Bose condensation is that the signal, huge signal because we deal with coherent precision, so the signal is uncomparable with the usual linear resonance, because we have the full magnetization which are deflected and processed coherently. So the signal is huge. So this is line amplitude is the transverse component of magnetization. So absorption plus dispersion, square roots of 12. You see, the signal made from different energies of pumping. If you have very small energy, you have just resonance here, linear resonance. If you increase the energy, then you can create the Bose condensation because the number of magnons big enough. And then properties, doesn't matter what power you have applied, the signal is always exactly the same. Just only the moment when the signal destroyed, so when energy is not enough for support number of magnons, correspond to different angle of deflection. So here is amplitude which is correspond of angle of deflection magnetization, sinus of deflection of magnetization, and this is the frequency shift. Why frequency shift? Because you need the non-linearity. The frequency should be shifted, and frequency should depend from the number of magnons. If frequency depends on number of magnons, it means that we have chemical potential, which energy per one magnon, and this is extremely important. If you have not interaction, then you have not Bose condensation. So, in case of Hahn echo, there is not Bose condensation because there is not interaction, or it's very small. Okay, so induction decay signal without Bose condensation is short. For this case, in the case of Bose condensation, each order of magnitude longer. Now, the same was found in antiferromagnets with Sul-Nakamura interaction. Sul-Nakamura interaction is the interaction between nuclear magnetic resonance of nucleus and antiferromagnetic resonance of antiferromagnet itself. There is crossover, which give the frequency shift. So nuclear magnons interact with electrons, and as a result, electrons give the interaction between magnons, between nuclear magnons. This interaction has the repulsive property, so we can create Bose condensation, and it was successfully done in 2012 in Kazan University. So, what else? Just recently in Kazan University, we have found exactly the same properties. You see that the signal doesn't depend from the power, but only depend on the frequency difference. We have seen in yttrium ferrite granite. So, in yttrium ferrite granite, we can make not gas of magnons. We can make the liquid of magnons. And this liquid is coherent, so it's superfluid of magnons liquid. It means that the same phenomena we can done in just ferrite films. How it looks like. So, you see, we have two, for example, we have two ferrite films, and the bridge between two. One, we can make the Bose condensation with one phase of precession, and other with other phase of precession. And then, in the bridge, there should be current. So this current is huge, uncomparable with the magnonic which used now. And it should transport magnetization, but superfluid way, not usual spin waves gas. So, what we can do, if we have decrease of this bridge, then we can see the Josephson effect. We should see the Josephson effect. If we have made, for example, Josephson bridge and the big channel between two films, then what we have? We have a squid. If you know, a squid is the quantum interferometer on the base of the Josephson effect in superconductors. You have the loop of superconductors with one Josephson junction, and as a result, you have changed the magnetic field coming through this equipment. Then the circulation of electric current, supercurrent, changes, and we can measure the magnetic field. Here's the full analogy. We can make the circulation of magnons, which will measure the flow of electric current through the hole, one-to-one. So, we have many advantages for this superfluid magnonic current comparable to the usual magnonic phenomena. First of all, the magnons, in this case, has a minimum of energy at K equal to 0. Okay, I have some kind of remarks which I don't tell. So we have working in other case than previous, the other case of orientation of magnetic field. In the magnonic experiments made just currently by different laboratories, the magnetic field was in plane. And the magnons have a stable conditions when we flow along with the magnetic field, because it corresponds to minimum of energy. But if we have put magnetic field vertical, then we have a minimum of energy correspond to K equal to 0. And we have exactly the same properties as in other Bose condensate. So K of magnons is equal to 0. So it's homogeneous precession. And as a result, we have integrated signal. We have not some kind of the oscillation of magnons because of its flow through, but we have the huge signal of all magnetization deflected on big angles. Secondly, if you have changed the magnetic field, you have changed the angle of deflection, you have changed the signal. It means that if you have, for example, the transformer, magnetic transformer, then the signal coming through this film depend on magnetic field, and you can just simply by magnetic field can change the amplitude of signal. So it's straightforward. It's transistor. Then we have made. Okay, we can control the frequency of pumping of magnetic field. And then, just because we have the loop like this, what is it? it's typical quantum memory. So, of course, it's just first ideas, and we can make a different type of quantum memory on this phenomenon. And so, it looks like all this my talk, or this my ideas, and we have applied it in Kazan for try to found the Bose condensation, and Timur Safin will be presented the result in his presentation. But point is that we have applied to one of the grant, and one of the referee wrote that there is many specialists of magnonics in Russia, so we have not need a French guy to come here to do the magnonics. And secondly, that I don't know any book about magnonics. So my answer to commission was, come on, I have made magnonics, real magnonics of superfluid magnons in helium-3 just 30 years ago. And they do now usual magnonics, uncomparable, weak, incomparable with this one, but at room temperature. Okay, let's turn from superfluid helium-3 to yttrium filigranate, which is not so good as helium-3, but nevertheless also very clean, very long time scale of magnons live time, and so on. And just show that magnonics exist 30 years. Magnonics exist, or Bose condensation of magnons exist even before the Bose condensation of atoms. And this is why we have started to make publicity for this phenomenon. Thank you very much for attention.
Now, please, questions for the lecture is open for discussion. So, please, questions. Thank you very much for this exciting, excellent contribution. Of course, I have to excuse because I do not understand all the depths you have mentioned. But I have a stupid question. Please excuse me. In which relationship your wonderful work is related to the topological phase transition, which also dealing with very thin layers like helium-3 at low temperatures? Is there any theoretical relationship? Can you comment? Because this is an exciting phenomenon. It's a Nobel Prize in this year.
Yes. Your question is so clever, so I have a few answers on it, because it depends what really question was about. So, helium-3 is a topological isolator. So, in the surface of helium-3, the gap drops down to 0. And the Majorana fermion should exist on these conditions, as was predicted by, I remember, Grisha Volovik, and before him also prediction by somebody else. And what should happen with this Majorana? Of course, with cooling, the Majorana particles, which should exist on the surface, its density decrease. And energy, of course, decrease by power law, T-2 or T-1, depending on the conditions. And we have also the superfluid helium-3 bulk, where is the Bogolyubov quasi-particles. They are many, they are energetic, they are above gap, but with cooling, if we cool down much lower than the gap, 20 times in our conditions, then they died. They frozen, so heat capacity of bulk decrease exponentially. There is temperature when there is crossover between energy stored in the quasi-particles, Bogolyubov, and energy stored into the Majorana. In experiments in Grenoble, we have succeeded to see this crossover between these two processes. So let's say we discovered the Majorana in superfluid helium-3, because all properties correspond well to Majorana properties just from point of view of heat capacity. but it's not related to the magnons. It's related to the other particles in helium-3, Majorana.
Yes. But you may explain the properties of these very thin layers and also the coherent quantum state to this your model, this your theory.
No. No, because Majorana has some people try to see it by acoustic waves. Of course, they should have the magnetic properties, but the layer is too thin. The sensitivity is too small, and as a result, magnetically, it may be some special experiment in future which may found it. Problem is that that you have, when cooling, you have small heat capacity of quasiparticles, but magnetic moment of bulk remains. So magnetic moment of bulk uncomparable with magnetic moment of Majorana. So by magnetic resonance, well, you maybe need to make the film of very thin film without of the bulk, but then it will not be, I'm not sure that it will be Majorana after this, because they need the properties of the age. If you're not other side, you have not age. You have just flow of the helium-3 normal, because it's not yet enough thickness, but without of the main density of helium-3. So I guess the magnetic resonance in this case not very good idea.
Thank you very much.
Any more questions? Yurii Bunkov, I have a question. This phenomena this phenomenon is quantum phenomenon.
Sure. Yeah.
And you say all magnetic phenomena are quantum.
Yes.
Phenomena. Yes. But we use precession of magnons. But precession is a classical notion. Huh?
Yeah, it's a good question, and I have the very nice answer. Huh? I can say it like this. You see, in the Middle Ages, we have the geocentric world map. And in this geocentric world map, the whole trajectory of planets can be very nice calculated. No problem. It's very clear geocentrical world. And then some guys come and said, no, we should take the heliocentric world.
Yes.
Come on, we have calculated here beautifully. All professors teach to these things. Why teacher should change his mind? No, never. Let's Giordano Bruno fire. That's exactly the same. You see,
It's maybe not correct, but convenient. Yes. Yes.
yeah. I told that many phenomena in magnetism can be explained just by simple approximation of solid body rotation. If, say, more theoretical way, you can say that the magnetic ordering has a matrix of density with diagonal terms and non-diagonal terms.
This is statistics.
Not necessary statistics. And then you have if you have statistics, you have diagonal terms which determine the orientation, and non-diagonal terms is just zeros.
But
Then if you have excite something,
the apparatus of
density matrix.
is statistical apparatus. Yes.
Come on, we can make it some kind of the instant presentation. If you have interested, for example, deflected magnetization with process.
Yes.
So you have non-diagonal part of these things, And you still have presented
macroscopic
macroscopic. Yeah.
system.
Yeah. But then, if you have compared the matrix of density in one side, place and other place, you usually have no any covariance. Only for diagonal terms.
Yeah, yeah.
And non-diagonals are not covariant. This is the usual magnetism. If you have the coherence of non-diagonal terms, long-range ordering, according to Feynman, this is a quantum phenomenon.
Thank you. Any more questions, maybe? No. Thank you very much again. And now.